Thank you very much for the invitation to be here. So this afternoon, I'm going to discuss a behavioral approach to design and the way this relates to an architecture of strange specificity. And I'm going to try and illustrate this through the work of my practice studio, Roland Snooks, as well as the research lab that I direct at RMIT University. So at the core of this work is a design methodology that I describe as behavioral formation. So it's an approach that draws from the logic of swarm intelligence and operates through multi-agent systems. So this is a strategy for encoding design intention within a set of computational agents, distributing design intention, and through the interaction of those computational agents, some type of self-organized intention emerges, and a type of complex architecture is drawn from that system. So essentially, this work is all about the relationship between emergence and intention. And it's something that I tried to distill and describe in a PhD that I completed about 5 years ago. And when I started writing this PhD, I thought I was writing a PhD that was somehow trying to describe an architecture of swarm intelligence, as though it's some type of generalizable model that could be described and then perhaps disseminated and adopted. But then by going through the act of writing the PhD, I realized the things that I find compelling about the projects is not the abstraction of process, but it's actually the specificity of the things themselves. Like, it's the strange qualities and characteristics, the things which exceed their process, the things that can't be described in an indexical way. And so what I'm going to try and do today is to walk through some of this work and try and describe how some of those characteristics and behaviors have emerged. Intrinsic to this is an interrelationship between self-organization and a series of other things that disrupt self-organization and emergence. And part of this is about the different roles of intention. Part of it is about different types of agencies, between computational agency, the agency of material, the behavior of robots, gestural or painterly operations, how these all begin to come together to create an architecture which is not something which can be simply indexed back to the algorithms which are in part drive the work. Perhaps the easiest way to describe what I've been working on is through a project. So this first project it's the smallest project we've made. It was designed for the Côte de Le Monde exhibition at the Pompidou about a year ago. And it's probably the most purely algorithmic of the projects. So I'll try and describe this behavioral approach through this, and then unpack how that starts to get disrupted, or what sort of impurities begin to emerge in subsequent processes. So this is the type of generative algorithm that we've been using. And I describe this algorithm as a manifold swarm. So it starts off as a cloud of disorganized points, and through the interaction of these agents, some type of higher level of order begins to emerge through their interaction. And you can see in the second animation, each of these agents has a type of geometry, and I describe that as a body. And I'll talk more about that later. So in this particular simulation, you can see there's several levels of generation. One that's generating the overall form, and then at a smaller scale, there are these finer levels of interaction, which is generating these unraveling, sort of delaminating surfaces. Where each of these agents has a body, in this very subtle animation, you see how their limbs start to join and connect to each other. And this is an attempt to try and create continuous lines of structure and also certain expressive effects. The work we do, of course, is developed through algorithms. So it's coded. These are the types of interfaces that we use. And what we're doing in this case is writing the behavior for each of the agents, how they're going to respond to things that are immediately adjacent to them. And in doing so, and in this project in particular, it's generating a strange type of geometry that's something between surface, lattice, and volume. We've started to describe this as sort of a fibrous mass. And when we're generating things which are, particularly intricate, particularly complex, then becomes the issue of how you start to build this work. And a lot of what I'll describe today is how we've attempted to construct these types of geometries and how that started to infuse or affect the type of work that we do. This one's constructed very simply. This is laser-sintered aluminium. We've done a series of projects along these lines which a sintering aluminium or titanium. And it's a very small scale object. Each of the elements, there's about a 1.1 million elements in it. Each one's about 0.4 of a millimeter in diameter, so quite small. And there's a whole series of different readings at different scales of this. So at the edges, it's a it's sort of almost a frayed, feathered edge. As you move into the center of it, it becomes much more turbulent and thick and massive, I suppose. We're quite interested at what scale. This is all made from straight lines, of course. It's quite small straight lines. We're quite interested in at what scale you read something as straight, and at what scale you read curvature in the work, and at what scale the intricacy almost dissolves into a silhouette of the project. So this is, as I said, probably the most purely algorithmic of the processes that I'll show today. And the algorithm it draws from the work of Craig Reynolds. This is work that was done in the 1980s around simulating flocks, schools of fish, social insects. And it was a very clear demonstration of the bottom-up nature of these types of behaviors that are found in nature. Now, what we're trying to do in the practice is not try and make architecture somehow swarm-like or flock-like or natural or biological in any way. This is an attempt to try and use this type of system where we can think of behaviors and think of design intentions as very discrete set of rules or protocols or behaviors that interact with each other. And so it's an idea that instead of thinking about the overall, like all generative design, I guess, we're not thinking about the overall, we're thinking about the micro scale, how those decisions interact and what it leads to. And so these are some of the very first studies we've done, and this is work that we've been working on now for 17 or 18 years. And of course, we're interested in the way order emerges from these systems. So when we're designing, we're really designing algorithmically through these 4 different strategies, through diagramming. All these behaviors work on simple vector mathematics, writing of pseudocode, and of course the writing of actual code. And one thing that's important to point out is this is not something which is, it's not a binary condition. It's not saying an agent will do this or it will do that. But there's a whole series of different things that the agent might do, and they're all negotiating simultaneously. And so it's a way in which you don't need to think about architecture in terms of a series of a priori sequential hierarchies, but you can think about it as a set of weighted intentions. A lot of the multi-agent work that we see arising in architecture and other related creative fields think of the agent as a point, and points are, of course, extremely difficult to make architecture from. So we're interested in the way agency can be embedded in higher levels of geometry. So occasionally we're using it as a point, but more often we're using it as a control point on a curve or as a vertice of a network, or the one on the right is an agent body, and I'll talk about that a lot. That's had a kind of very large influence in the work that we do. So I want to quickly describe how we've used this over the years. So this first series of projects are all, I think, probably over 9 or 10 years old. The older projects in our work, and we've used this as a way of generating form and looking at the relationship between form and articulation and how these can be seen as a synthetic relationship, or the way that structure, form, and articulation might all come in, or be produced by the same algorithm and start to have a synthesis. Or the way these algorithms might be used to create these types of fibrous or hairy geometries. Or the way this type of algorithm might enable us to uncouple the relationship between geometry and element. And I guess Gilles talked about this a little bit as well, this idea that you don't have an architectural element that relates to an architectural role. And I guess the way I would describe it is, say in this tower, for example, the shell of the tower is partly structural. It's partly, of course, formal and provides a surface. It's sun shading. It opens up at certain points. It becomes spatial. If it got a little bit finer, maybe you'd be able to describe it as being ornamental, but perhaps it's expressive in some way. So it's one piece of geometry that does several things. So in this case, the architectural role of, say, resisting load is a behavior. And these behaviors operate and negotiate through this one piece of geometry. And then in the end, that piece of geometry ends up negotiating but also expressing the outcome of those different architectural roles and behaviors. So we've looked at this at several different scales. Another key concern in the work has been around the relationship between the bottom-up and the top-down. And so I think when Rob and I started Kokuja in 2014, we sort of had this very naive belief, 2004, we had this very naive belief that perhaps all of architecture could be generated from the bottom up through emergent systems. And of course, as soon as we started to attempt to do that on more complex architectural programs or projects, we realized that there's a whole lot of questions in architecture which are simply not complex ones. They're not ones that need self-organization, and they're actually much more suited to direct operations. So we started looking at what is the relationship between the top-down and bottom-up, and in this type of example, it was modeled originally as a single surface, directly modeled in a top-down way. Then it began to sort of self-organize and reorder in a bottom-up fashion. It's something that we worked on with Tom Wiscombe, an architect from Los Angeles. We collaborated on this project, and this became a much sort of messier relationship, and almost like symbolic of the way at the time our practice, Kokuja, and Tom were working quite different ways, and he was working in quite a direct way, and we were working in quite a bottom-up way, and this became this messy hybrid of the two, almost originally a Frankenstein, where these two different processes would interact, and over time, something would be generated and then be remodeled and then go back and be regenerated. And through this constant process, it came into some sort of synthetic relationship where it was hard to trace the project back to either explicit moves or generative moves. And then that also caused a blurring of geometry. And so in this geometry, it's a geometry of strands, I guess. And some of those strands are spatial and some of those are formal, some are structural, some are purely expressive at a very fine scale. And similar types of projects, looking at the relationship between structure and surface. So most of those projects were done 10 or more years ago. And I guess as I've seen computational algorithmic architecture change over the last, 2 decades, I've begun to realize there's a shift in this work from seeing algorithmic work as something which is speculative and experimental, almost to something which is stable and an act of selection. And I guess what I mean by that is that originally my interest in this work was to try and write algorithms, write behaviors in order to speculate on what architecture might be and what its possible forms, structures, organizations could be. However, what's happened now is a lot of the algorithms that are used have almost become they're so known and so indexical in terms of there's a very direct relationship between the type of algorithm and the type of geometry that's produced. So consequently, many of us, or many people within algorithmic design, now use algorithms as an act of selection. They're selecting an algorithm because they know what the algorithm will produce, and it's inherently no longer being used in a speculative way. And so I think a lot of the work that I'm now going to show, a lot of the later work, the work in the last 9 or 10 years, is really about how to undermine the indexicality of the algorithm, how to force it into some sort of negotiation or relationship with other agencies, whether they're sort of direct modeling, whether it's sort of painterly, whether it's got to do with material and fabrication, to see what it can create. So this is an example from a project from a few years ago, and this is looking at the relationship between self-organization and painterly operations. So how something is gestural, it goes back and is then reformed algorithmically, begins to self-organize, it's brought back out, it's sort of repainted and rebrushed, and we developed a series of these types of geometries. And I guess the aim with these geometries is to try and make something which couldn't be understood as being indexed back to its process of formation. This is something that we've also worked on with students. So this is, I think, probably the only slide I'll show today of student work. And this comes from a studio that I teach at RMIT. And this is the work of one student from, I think, several weeks. We'd normally ask these students to produce 15 or 20 of these objects every week. And what we're trying to do is ask students to really develop an aesthetic sensibility in terms of the way self-organization and painful operations might work. So another relationship, another way of undermining or subverting the algorithm is to take digital agency and material agency and put them into a feedback loop where they each inform the other. And so this is a project that was done in collaboration with Gwil and Cam, who I think are somewhere in the audience, from Hologram. And this was just an idea where in the top row, it's really about using an algorithm to design an object, and that object is then produced somehow, typically through robotics. By the time we get down to the bottom row, there's an idea that what if the robot and the agent were the same thing? And the reason for doing this is the robot and real-time feedback and vision systems become a way of putting computational agency and material agency into the same sphere in many ways, and what is the feedback between them. So it's a totally absurd project. It's a project where we have one robot that's squirting out foam, another robot which is scanning it. In fact, there's a couple of scanners that are used. And so what the robot sees is something like this. It's fairly low resolution. And typically when we're working through this, there wasn't a pre-designed model, but what would happen is the robot would extrude some sort of fairly disgusting foam, and then it would scan that, and it would make a decision as to how it's going to extrude something next. But you can see even in the very early studies, there's some sort of order emerging from that. You can see that it's not an entirely random thing. But what was interesting about it was that it created things that we didn't understand as either digital nor simply of this sort of spewing of foam, but it had a series of hybrid qualities and characteristics. I mean, these are not things that we would design, I suppose. But also, it had quite a range of characteristics. In these sort of 3 or 4 slides, you can see, I would say, a diversity of character. Okay. The rest of the projects I'm going to discuss are based on an algorithm that we developed about, I guess 10 years ago now. And this algorithm is an agent body algorithm. And basically what that means is the agent has a designed set of limbs or designed geometry. And each joint in that geometry, in this case there are small splines, each joint of that geometry has a level of agency in itself. So they can start to respond at a more micro scale. When we first developed it, it was for this. This was an attempt to make an ornamental ceiling for a design competition we were working on. And I guess in the project, there is a figure that starts to emerge from this field. But as you start to zoom in, then you see a whole lot of other conditions. So you can see some singular conditions on the left, sort of wing-like condition. Then there's sort of periodic repeating in it. There are parts which are near symmetries. And none of these conditions are written as rules or behaviors within the system. These are all emergent outcomes of the interaction of these agent bodies. And then as we begin to move in, zoom in further, a whole series of other characteristics and qualities are evident in the work. So when we did this in 2009, this struck us as being something which was strange, this particular image. And we tried to come to terms with what that really meant. And I suppose we saw strangeness as something which was not something we could immediately understand as being ugly or beautiful, but there was a hesitation in the way we'd evaluate it. And this became almost something we'd strive for. We'd strive to create things where we had to hesitate before being able to evaluate. Now, strangeness, of course, becomes domesticated, and this is something that now I feel is sort of very known, but didn't feel that way at the time. The first time we tried to use this algorithm in an architectural project was a competition for a memorial and museum in Kiev at Baba Yar. And so this consists of a landscape, a sort of stone-like museum, and a carved-out memorial space. And the landscape was seen as a charged field. I mean, it's an incredibly charged project in many ways. And we looked at the way agents might begin to navigate that field and create various different intensities and densities to generate a landscape. But then also, perhaps that becomes dense enough to then carve out a memorial space. So the project is quite unlike a lot of the projects I'll show today, and I have shown, which are all about synthesis. This project is deliberately about contrast or juxtapositions between certain things. It's a rock-like building that's sort of cantilevering as though it might be trying to fly, or it has a smooth outside skin and then a highly detailed, expressive, perhaps ornamental interior. That's the algorithmic diagram for the project. And this is really evident in the section. You see this contrast between the intensity of the memorial space and then the calmness or reflective nature of the exhibition spaces in the project. Okay, so all of those two agent body projects were really using the agent applied to something else. So it was either applied to the ceiling, it was applied to the inside of a space that was carved out. But what we were really trying to do is work out a way in which we could have an algorithm that would both generate space and form, but also generate its articulation, its structure, perhaps its ornament. And so this is when we started working on this algorithm that I describe as a manifold swarm, where it goes from a cloud of points to a sort of almost manifold surface. And in creating, this became a really critical image this was produced in, I think, 2011, and became a really critical image in the trajectory of the work. I guess when we made this, it seemed to embody a lot of those things. It embodied something which was the same algorithm created, space, form, structure, its articulation, but it was impossible to build. And so in many ways, the rest of this presentation is really trying to describe how we went about trying to build. It's what's become a personal obsession over the last 8 years now, to try and build a geometry like this. Not so much just to reify the digital, but really as a way of trying to understand how each time you solve one problem through new modes of fabrication, that has the potential to go back and fundamentally change the way you're designing something. And so perhaps that's what this presentation is. It's the story of that. So when we were first doing these types of work, this is for the Aalto University. It's a competition in Helsinki in 2012, perhaps. We were looking at the translucency of these, and we thought perhaps the first way of making these is through fiber composites. And so we went through a whole series of experiments. A lot of these were done through workshops at universities, looking at the way we could think about the strand as being one of these agent-based strands, but literally building it from fibers. And some of those were made in 2D and then wrapped into 3D. Some of them were made on molds. And I guess going back to Mario's question or comments about molds, I think a lot of the story is about that. I mean, how we avoid it and then when they're actually necessary. We're interested in the way that these might be expressive. I think there's, in the last, 10 or 15 years, there's been a renewed interest in architecture in fiber composites. And of course, the first fiber composite building that I know of was the 1957 Monsanto House of the Future. So it's actually really old technology. But architects such as Greg Lynn, more recently Akim Menges, have become more interested in these, I think largely because of the performative capacity of this material. I'm probably less interested in the way it performs and more interested in the way that it behaves, or the way that, what are its expressive capacities. So some of these are quite dirty, some of them are quite ugly things. Some of them, this one done by students at RMIT is more refined. And this was probably the first project in which we tried to bring this together and make it into a project. So it's a small object. It's about 2.5 meters tall, and it's an attempt to try and compress surface structure and its expression, or perhaps we'd describe it as ornament, into a single unified assembly that can't be reduced to its parts. So it has a fairly, what's probably now in this presentation becoming a familiar type of algorithm. Starts off as a swarm, kind of becomes a surface, and all these agent bodies begin to connect to each other and make continuous lines of structure. Now, in this project, there's a lot of, and they're compressed. There are these bodies that are compressed between layers of fiberglass. This is a detail of it. So this is something that's using digital fabrication. So, but we're actually using digital fabrication to make molds to cast things into them. And so, for example, here we made 3 different molds, cast 3 different flexible agent bodies, and we used polyurethane foam, which was flexible. It could bend, but it couldn't stretch. So then this became a behavior we had to then write into the generative algorithm. And so to ensure that the way the digital computational model behaved would be the same as the way the physical thing would behave. There's a lot of milling involved. We made a mold for the entire piece. You can see that each of these polyurethane agent bodies are pressed into the mold. They're coated on either sides with fiberglass fabric. This is then all vacuum infused, and it makes something which is, then the mold is thrown away, and I guess this reinforces Mario's point about the mold. I mean, in boat building, the mold costs normally 15 or 20 times the price of the part that comes off the mold. So if you're making an architecture which is entirely non-repeating, that's an incredibly inefficient way of working. It's also incredibly sad if you're the one that spent weeks sanding this mold to then hack it off with a blade and throw it away. It's also incredibly wasteful. But in the end, what we're left with is something which is very thin. This is less than 1 millimeter thick, the fiberglass, 0.85 of a mil. And it gets its structural strength. I mean, it's basically very, very flexible. The surface, the agent bodies are very flexible. But when you take these two flexible things, they come together and make something that's very strong. And the reason is it's getting strength through geometry rather than strength through material. And what's happening is the foam body is giving a structural depth of only about 1 centimeter, but that's more than 10 times the depth of the fiberglass. And also you can see that because these bodies are connecting to each other, they're making these continuous lines of corrugated structure. And we're also interested in the translucency and transparency of these. Then we were asked to scale this up. A client came to us and said, would we build this exhibition design, which was about 10 times the size of that previous project, which was 7 square meters. This one is close to 70 square meters. And it was for the RMIT Design Hub. And so these are the digital models of that before we started to rationalize it. And then as we started to rationalize, and then these are some of the prototypes that we made. This is the vacuum infusion process. We realized that we couldn't make a mold that's 70 square meters because of the cost of it. Yet we're trying to make an architecture which has not obvious repetition in it. So in order to do this, we made it out of 8 pieces. 3 of them are flat, very easy to make. 5 of them are curved. And each of these curved pieces come off the one mold. So you can see here that the gray is the mold. Each of the white profiles are a different, I guess, part of that mold, which is used to make the parts. And the idea is they come together to make a family of forms, where the repetition is not entirely evident, but there's some sort of repetition of character in the project. Mold making is complex and difficult. There's a lot of milling involved. This piece is about 1.5 meters across. It's a very small part of a mold that's partly made manually, it's partly made robotically. It's almost a small architectural project in itself. It's about 5 by 6 meters, almost 3 meters tall. And there's 2 levels of structure embedded into this. And one is a large scale made from rigid foam. Another one is a small scale extruded from silicon. And these agent bodies are responding to structural imperatives. And I guess one thing I want to point out is that none of the work that I'm doing is driven by structure, but it's always, because I see structure simply as an issue of building science, not important enough to drive architecture, which I think is fundamentally part of the humanities. But it's something that always conditions what we do. And so this is a diagram of the bending moments within those surfaces and the way the agent bodies start to realign in response to the direction of those bending moments. So the rigid foam was difficult to mill. It had to be milled a backside, then jig had to be milled, then topside had to be milled. So very laborious for the poor robots. This was much easier. This was just extruding silicon almost out of a kind of crude caulking gun that we fabricated and stuck on the end of the robot. This is Cam in some poor working conditions, trying to work out how to lay out these one-to-one prints and drop the foam in, and even worse working conditions for the boat builders. These guys used to make hulls, carbon fiber hulls for American Cup yachts, and they said that this was the hardest thing they had made, which clearly is a demonstration of how poorly or how wrong we were to try and attempt to make something in this fashion. And anyway, it's coated in fiberglass. They're trimmed down, loaded onto the back of a truck, installed in this case at the Design Hub in Melbourne. So they have a smooth side because the molds reused, and they have an articulated side, which comes off the top face. And then this was reshown in in Shanghai at the Biennale. I guess I was trying to labour the point there that was difficult and not really a sustainable way of developing this type of work. So we took a step backwards and said, okay, how could we create these types of forms and geometries through a simpler method? This was an attempt to try and make it through flat sheet material in a way that you could just take small pieces of metal, laser cut them, and when you would rivet them together, they would find their own double curvature. So it's a way of unrolling a three-dimensional thing back into 2D and backwards again. We made something similar. So the last time I was in Tallinn was 4 years ago, and it was for the Biennale also, where we exhibited this small piece, which I believe is still in Tallinn, knocking around somewhere. I think somebody wants to get rid of it. I have to take it home with me on the plane now. But it's actually in 3 parts, so you can they nest together. You can take it on the plane. That's the way it came here. This is a very, very thin fiberglass. This is about 1/4 millimeter thick. It's made through the same process of putting together the black skeleton, which is, in this case, glued together, and then vacuum infused this very thin layer of fiberglass to deal with all the shear forces in it. And then this was sort of curated into the exhibition 4 years ago, where we're sandwiched between Tom Wiscombe and Akim Menges. And I think there's sort of a conceptual as well as spatial sandwiching going on in the work. Now, the problem with this project is I started off by showing that first animation of this very thick, dense, fibrous mass, and now we're left with this very, very thin surface. And in some ways, it's sort of, that's what's been lost in the project, being compressed down to a surface, and I think a lot of its spatial quality has been reduced. So we started working on these types of projects, this idea that could we start to build the fibrous lattice nature of these geometries, and could we do it through metal rods? And so this is a project where we have 2 little robots which are grabbing metal rods and they're bending them. Of course, there are CNC rod bending machines we could have used, but we don't own one of those, but we do own little robots. And so this is the type of, I guess, intricate spatial implications of that. And what we were trying to do is we're trying to understand what the robots can and can't do. What they can bend, like how far they can bend, how many bends in a certain direction they can do, what's the distance between bends. And these are all parameters of the behavior of robots. And we needed to understand those to then go back and encode those in the generative algorithm. And the purpose of this is that the geometries we're creating are volatile, they're fairly wild, they're very hard to go back and fix up or rationalize. So all the construction information, all the way that these things are built, you must know before you start designing them and then build them into the generative algorithm so that you know that whatever is generated is inherently going to be built. Now, we optimized the wrong thing in this project. So those robots spent 1 day and they bent 270 rods. Every one was unique. But then we had 5 people spending 5 days working out how to put them together and weld them. And so we realized that the problem here was not so much a problem of fabrication, but there was a problem of assembly. We also then went on to scale this up. We got bigger robots and bigger bits of metal and made a pavilion in Shanghai. But really our ambition is not to make these small objects. These are all sort of proto-architectural. They're things that want to become buildings, or in this case, we would like this to become a bridge. But I guess by trying to prove at the small scale, this thing is in some ways an efficient way of making something and a realistic and a feasible way of making something, then perhaps it's not entirely ridiculous to make something that looks as whimsical as this does. So I guess I've just described the projects going in a series of different directions, each of which developed their own limitation or problem. And this became an important project a couple of years ago in trying to bring those problems back together. And so you can sort of see in the work that we have an obsession with certain formal types, like we're obsessed with things that are rock or boulder-like. We also had an obsession with these wings and this fibrous mass, these networks. And this was a project that tried to bring them together, but it had to radically change the way we thought about the fabrication of it. So this is an algorithm which it's trying to unfurl like the other algorithms, but it's also constrained, in this case, by these boulder-like forms. So on the outside, they have a very hard silhouette. On the inside, they're starting to delaminate into a series of almost flaking geometries. So it shifts between surface and lattice, which is sort of evident in the section. So in order to be able to do this, we realized we need a different methodology. All the previous projects, we were thinking about how do you build the network of agent bodies. And then we realized that that all our attempts to try and build them, we either needed molds for them, or we needed to, or we could make them as networks, but we couldn't surface them. And then this shift in thinking was that, well, perhaps what we should be doing is we should be fabricating the surface and then casting back the agent body structure into it. And so that's when we started looking at large-scale 3D printing. And so this is a print where we're printing a thin skin, and then we're casting into it. You can sort of vaguely see in these images a series of conduits, largely vertical conduits, which we were then using to cast concrete into. And so this is a fiber-reinforced high-strength concrete. This is obviously a render. And then some of the prototypes we developed for that. So in many ways, this was able to bring together these concerns around different formal types, different structural types, and also in a way that was highly efficient and I guess dealt with the problem of the mold. So in this way, what happens is the skin is the mold. And so you don't produce a mold that you throw away, but instead you have a sacrificial mold that you simply cast into. And then that project had a sort of a younger sibling, this small project. For public art project. Okay, so that was really an attempt to try and resolve a problem we'd invented for ourselves through computational design. But it really didn't relate to the way 3D printing works or what is efficient or effective to 3D print. And one of the things we realized when we started printing large-scale architectural elements is that it's much more efficient to print something where it's a continuous toolpath. You're not stopping and starting, which means there's a limitation to the topology. You're basically limited to sheet surfaces. And so we decided to try and design through that method. And this is an algorithm where basically we have a continuous sheet where it's a mesh, and each vertex on that mesh is an agent, and they start to interact. And through all these interactions, the surface begins to crease and fold and crumple in various different ways. And so this again is some of the prototypes from that project. And this is a screen grab from the algorithm, and you can begin to see how these agents are creasing or crumpling the surface. And it's most evident perhaps in the section, where you begin to see it's creasing and folding the most where there's most structural load, so on this arch at the center of that section, and then it's starting to corrugate towards the tips. So it's corrugating in the direction of the cantilever in order to resist the load. So it's a sort of logic where we're combining, again, form and structure, but it's not really about structural optimization. It's simply about structure conditioning what we're doing. And so this ends up having sort of these three corrugated wingtips. This then became, I guess, this led to the first of the built projects that we 3D printed. It's a very small project. This is part of a facility called SensiLab. It's at Monash University in Melbourne. And so it's a research laboratory where my office designed the interior for, and I'll talk about that briefly. And then we took one very small part of this and 3D printed it. And I guess the challenge, or what was interesting for us in this project, was just simply trying to get 3D printing through fire codes and building codes. And there's a lot of skepticism when we began about, can you get transparent polymers through all these codes? And I guess the answer is that yes, eventually we were able to do that. So it's part of this building. It's an existing building built in the 90s by quite a good architect in Melbourne called DCM. It has this curved black wall with these sheared openings. And so we basically developed a series of these objects that would sit in this this almost warehouse-like floor plate. We sort of gutted the original building, and then each of these objects sort of lean into the angle of the walls. And so there's a series of different workstations and hot desking and different office spaces that goes between these objects. And then each of the objects have a very specific technical role. So one is a sound recording studio, there's a cinema. And the patterning comes from a similar strategy to the way we make the objects. So the objects are their forms, and those forms get booleaned to make a series of openings and a series of, I guess, parts that are carved out from them. But then there are a series of virtual objects which boolean through and then create this patterning. So as you move through the space, these objects become in and out of focus. So some of them are smaller objects. Some of the spaces become more carved, like this space, where they start to carve out, in this case, an exhibition space with a series of steps or display areas. And then this is just giant capital, much bigger than the column, which has no purpose. But a detail of that is part of the reading is I'm trying to make these things look entirely solid, and so there's no joints at the corners, and this led to a very kind of complex set of jointing details, which I won't go into. So inside each of these objects, as I said, there's a different technical requirement in each one. This one's a sound recording studio. And I guess this is, this is a moment, I guess, where I've got to admit to a certain hypocrisy in the work, and I start off by saying that I'm entirely against the selection of known algorithms, because I think they're indexical and they're entirely unspeculative, and that's exactly what this is. So this is obviously a reaction diffusion algorithm, which happens to work well with the refraction of sound, so we've used it. But I think it looks quite good. So at a certain point, you can kind of give up your ethics for aesthetics. It's a little bit hard to see on the screen. I apologize. It's too bright in this room. But there's sort of a highly detailed surface, and there's a series of these light lines that go between the surfaces. So there's a lot of different prototyping going on with this work. I'll jump through this quickly, since it's undermining my argument. But this is the, I guess, the more, to me, the more interesting part of the project. And it's a very similar algorithm to the previous project. There's a couple of levels of agency here. There's sort of large corrugations and smaller corrugations on those corrugations. We printed this at RMIT University. That's one of the larger panels. And these are some of those panels being produced and then installed. So there's a total of 10 panels with sort of expressed vertical joints, these zigzagging joints. And it gives you some sense of the sort of space and light inside it. And we're quite interested in the way that these types of geometries would refract and reflect light in different ways. And then the joint was the problematic part of this project, and we're sort of now addressing how you might deal with that. One of the curators from the National Gallery of Victoria saw this project and immediately sort of understood it to be ice-like in some way, and commissioned us to do a project at the National Gallery, which was this project called Flow. And so this was commissioned as part of the Triennale, and it was designed to only be there for 10 days, but it's in the sort of the Great Hall of the National Gallery, which, contrary to Gilles' suggestion that the best building in Melbourne is the NMBW garden building, I think this is the best room in Melbourne. I mean, not my project, the existing room. And it was a collaboration with a sound artist, Philip Smartsis, who has these amazing recordings from the Antarctic. This is Philip, and they're recordings of glaciers and ice cracking, and then he's sort of mixed that together into a 16-track sound work. And what we were asked to do is try to make a space that somehow captured the atmosphere of where that came from. Somehow captured sort of an ice-like or atmospheric Antarctic atmosphere. So this is the project. Some of the shots of it, and it's very different from the daytime to the nighttime. And this was open till midnight each night. And so there are three parts to this really. There's a polymer tower. There's a steel structure that goes into that, and then there's a timber base. I'll talk about each of those briefly. So there are about 70 of these panels, and which are 3D printed. And I guess it's quite a, it's a very, in some ways, pure thing in terms of its whiteness. And it sits in this room, which is incredibly rich, and has this amazing ceiling by the artist Leonard French. And then at a certain point, it sits within that as a foil to it, but then also frames that ceiling. It's a detail of the panels and the way they overlap with different translucencies or different levels of gloss on them. And so it's a swarm, I guess. It's a swarm of these panels. This is us doing some printing for it. So they printed fairly quickly. It took about 4 or 5 hours to print. This one's also, I think Mario's gone to sleep maybe, but this is also for Mario. You made the comment that it's as easy to produce everything differently if you're using additive manufacturing. And it's sort of true. One of the things we realized is that if each part is quite different, then there's a lot of risk and a lot of effort has to go into the digital side. Even though it's just as easy for the robot, it's a lot harder for the person. So this project was under incredibly intense time pressures. The whole thing had to be designed and built in 3 months, and it was only up for 10 days, so it couldn't be 10 days late. And so we made every panel very similar. There's very little differentiation in them. And it's to ensure that if we knew that one panel would work, then all of them would work. And so it's a type of sort of de-risking of the project. And it had this intertwined steel structure between the panels, so you can sort of see in this image. And we're trying to make something which was neither a steel frame which was clad, so we're trying to intertwine structure and skin. So it's an unrolled version. I'm out of time, so I'm going to speed through this stuff. The structure was developed in conjunction with Bollinger Grumman, who've done most of the work I've shown today, and CNC brake press folded. And that sits on top of this timber base. And so, which is 5-axis CNC cut, a series of ribs, and to make these sort of 9 relatively large objects, which had to be assembled in 3.5 days on site. So the timber went to, I can see why Gilles' interested in timber, it goes together very easily. The real problem was this bit when we had 300 individual different pieces of metal and 70 of these panels. And so we worked with the guys from Fologram, and Cam came down, and to avoid having to make drawings for this, we overlaid, of course, the holographic model. And so these are the guys installing, amazing installation team. They're all artists in themselves, and they install at the gallery. And it was a way to be able to work out how to position these elements. Maybe I'll just... Anyway, that was a video showing how that all worked. But maybe an easier video to watch is this one, how it quickly went together in 3.5 days. So the base went together easily. The next bit's got a little bit more difficult. The real problem with this is because we're trying to intertwine structure and skin, we couldn't just build the structure first and then build the skin, but the structure and skin had to go up together as one element. And so this was just-in-time completion, so you can see the painters are just finishing as the people arrive. And that was the opening. And there were about 85,000 people went through in the first 10 days of that project. And so then the gallery kept it up for another few weeks in the end. Okay, I'm going to finish by showing very, very briefly 3 things that are under development. Well, this one's not under development, but this one is a project from a couple of years ago, which, if the NGV project was about de-risking, about making the panels similar and simple and taking the risk out, this is really an attempt to try and bring some of the painted operations back into this type of 3D printed forms. This is a project that's currently, it's currently on hold, but it's a project in the office that we're doing in Portugal. And each of our projects seem to scale up. So if the SensiLab project was 20 square meters, NGV was 80, this one's 360 meters, so it's getting larger. This is designed to have a steel structure backing into the plastic. And the last one I'll show very briefly is this is a current project that we're building for the Shenzhen Biennale, which will open in December. And this is where we're starting to embed carbon fiber. So we're sort of going back to the fiber composites. This is embedding carbon fiber into 3D printed elements. So this is a small prototype of one of the joints. We've started to print this project. We're sort of about 4 panels into what is about 30 panels. And this is one half of that project. So these 2 wings that will form a space. And I guess in many ways what this is trying to do is it's to try and tie together a whole series of concerns that we've developed throughout the projects and in terms of being able to remove the mold, be able to embed structure into the project. And I guess one of the things that I want to conclude by saying is that, Mario, one of your comments was that we can now simulate things like structure, and we can simulate to see whether something's going to work. We can test things very quickly. We can, I guess, virtually prototype thousands of times. And I think that's absolutely correct. I think that's really important. But I think the other thing is that it's when you actually go through and build the thing, you realize the thing that you optimized was not the right thing to optimize. And it's actually by going through and building it that something else is revealed, which then changes the way you think about the design. And I think this is really, what I've tried to describe is the way that this is a little evolution of design projects, which is only really possible by the iterative failure, by doing them, by inventing problems for ourselves, and then these absurd ways we go about trying to resolve the problem actually leads to what I think is hopefully a sort of interesting set of characteristics and qualities to the work. Thanks.
Thank you, Ron. We have 8-9 minutes for questions.
Hello. So thank you for this very interesting talk. Very impressive images and things like. How far would you describe yourself as digital sculptor? Because obviously it's a little bit more on this design area and with pavilions, and you're talking a lot about structures. In the end, you have some kind of shape, so you start to design it at some point and make decisions, which is good, which is not so good. How would you describe yourself as digital sculptor?
I think it's a very difficult question, and it's a good question. I've always thought of myself just as an architect, and and I think all the things that I've tried to talk about and I try to do are inherently very architectural things. Like they're dealing with what is a relationship between structure and ornament, or what is the relationship between surface and structure, and so I think there are all these things I like to think are inherently fundamentally architectural things, even if they're exhibited in a gallery. Now, having said that, I've also begun to, of course, realize that these things are becoming more sculptural. And I guess the longer they stay away from the restrictions of architecture, the more they begin to deviate from architectural norms, I suppose. So I would never claim that they're works of art. I would never claim that they're sculptural things, but they're becoming more and more expressive, I suppose. So the ambition for them is to be architectural. Yeah. I don't know if that answers your question.
Could you pass the mic? Oh, yeah, sorry.
They're really fascinating explorations, and the kind of exploring of new formations. I don't like to mention it form. I started to be a little bit skeptical when it started to look like we open a body and see a heart, and it becomes a building, and we see the veins on the glass. So there is a reference to organic material once we open the body. So it starts to have a metaphorical effect, although it seems to be that you want to shy away to any kind of meaning which could be projected upon it. So it seems to be you value foreignness, that's also in your title, strangeness, but that kind of strangeness is a very different strangeness, which, for instance, the Russian formalists use, where the strangeness was used to open up language, to break it, to break the norms, and to raise questions. So I'm actually very interested what that fascinating explorations which produce this, call it new forms, new formations, what you imagine they in fact produce or could produce. Because words you don't use is the world is burning, is ethics, is climate change. Well, in fact, I think that the formal language you are producing, and then I think you become an architect, that they could contribute and bring a very valuable help with, for instance, landscape architecture. So my question is, how do you see, or what kind of potential do you see in the foreigners you are producing in this new kind of ornament?
Okay. I mean, you're right in terms of there's absolutely no deliberate attempt to sort of metaphorical attempt. There's no attempt to try and make reference or meaning in the work. I think inherently people read things into it though, which is I don't see as a I'm not concerned about that. Like I don't see a problem with that. I think the projects which are more charged, like the way people have talked to me about the memorial that we've done and that sort of bronze interior, people read things like that as like burning bodies or a whole lot of other things people read into that. It's certainly not. It's not intended in the work. But I think in some ways there's a whole lot of aspects to architecture which have been suspended deliberately to try and resolve a set of problems. And all of these. The first half of my career, I guess I was trying to design buildings, and they were all unbuilt. And then I guess the second half, I mean, so I'm an expert at losing competitions. I've lost 45 competitions, architectural competitions. If you want tips on that, I can tell you how to do it. But then after that, I guess part of that, the frustration of those things not being built, and they were never intended to be built. They're obviously whimsical projects. Then retreating back into making things which are small to try and prove a point and prove that these things can be done at a tectonic scale. I guess the ambition is to relaunch that back into architecture. And as soon as you do that, then it actually has to engage with a whole lot of questions which are much greater than this very myopic concern for tectonics, which I currently have. So I don't have an answer for your question, but I should have in several years' time. So perhaps next time we meet, I'll endeavour to answer your question. But I think once this is actually engages fully with architecture, it has to engage with those things. Yeah. So.
Good. I think we are well in time now. Thank you very much.
Pleasure. Thank you.